Well, hello, CP Math One. This is Mr. Roberts at Shasta High School, and I'm setting aside this time to walk through the Chapter 2 study team test that we took recently. This Friday, we are taking our test on Chapter 2, Friday what are we at? The 28th of October. And let's go ahead and go through these problems and take a look at them. First question. It's question one actually asks us to come up with the equation of a line that matches some given information, right? So there's enough information here to determine a line. What is the line? The first question says, hey, this line has a slope of 3. The slope is 3 and the y-intercept is 5. So just, review y equals mx plus b. There are two parameters for a line that are written in this form. We can write pretty much any line except for vertical lines in this format. And our two parameters are what's our slope, right? The slope parameter. And the other parameter is the y-intercept parameter, right? That y-intercept occurs when x is 0, right? And that value b is what pops up in there. So because I'm told both of these parameters, literally I'm told what the slope parameter is, and I'm told what the y-intercept parameter is, I know the equation of this line. It's y is equal to 3 times x plus 5. So pretty straightforward. That was pleasant. Next question. It says, hey, this line has a slope of 3/4. So we know our slope parameter, right? M is 3/4. And it hits this point. It goes through a particular point. The point that it hits is when x is 8, it'll give you back y is 10. So here's the technique that we've talked about. Because this is a line that has a slope that's not undefined, right? It has a slope of 3/4. I know that I can write this line in this format. And I know my slope already. What I don't know, right? I don't know my y-intercept parameter. So I need to figure out what that is. That y-intercept parameter I can find by plugging in a point that I know and solving this equation for b. In fact, I could pre-solve this equation for b by just thinking about, here's the equal sign. I'm going to subtract mx from both sides. So if I subtract mx from the left-hand side, it becomes y minus mx. And over on the other side, it's just b, right? So literally this says, hey, your y-intercept, if you need to know your y-intercept b, here's what you do. You take an x value and a y value that you know, and the slope that you know, and you just plug them into this, y minus mx. Well, it just so happens that I know a y value, right? I know a y value. And it also happens that I know an x value. I know an x value. And we were told quite generously what the slope is, right? We were told the slope is 3/4, so I know the slope. So to calculate my y-intercept b, I'm just going to plug what I know into this. I'm going to say 10 minus my slope of 3/4, right? So it's always subtraction, 10 y minus mx. So 10 minus 3/4 times 8. If you're unsure about arithmetic, right? There's no reason to not do this, right? Go ahead and use your calculator, right? I know 8 divided by 4 is 2, times 3 is 6. This is 10 minus 6. It's going to be 4. But if you're not sure, just run this through your calculator. So 10 minus, and I'll just go grab 3/4. There it is, 3/4. And I'm going to multiply that times 8. 10 minus 3/4 times 8 is 10 minus 6, which is 4. So I know 4 is what? It's my y-intercept. Oh, this is fabulous, because now I know both my y-intercept and I know the slope. I'll write the answer right here. I won't write it in the answer space for this video. I'll just write y is equal to m 3/4 times x and then plus the number 4. This is my answer. Now, I can check this a little bit, right? Because I know it has to have a slope of 3/4, and it does. The other thing that has to be true is if I give this an x value of 8, if I put 8 in here, it has to become 10. And if I'm not entirely sure, I can just, hey, grab 3/4. Oops, grab 3/4. There is 3/4. I can multiply 3/4 times the number 8. That's the input to this function. And then I can add 4 to that. And sure enough, 3/4 times 8 plus 4 is 10. So what I know is that if this function receives the number 8, right? If it receives the number 8, it gave me back the number 10, right? So this totally checks, and this is the equation we were looking for. The next one says this line goes through points A and B. What's nice about this is it's pretty easy to read the rise and the run pattern. So this line does have a slope of up 1 over 3. And also, I'm going to say it's got a y-intercept at 2. It looks like that's the intent. So in fact, I could go up 1 over 3, and it absolutely would hit that point, right? So I don't have to overthink this one. This one is y is up 1 over 3 times the x, right? That's m times x, and then plus a y-intercept of 2. So that is the answer for C. And then our last one in this group says this line is represented by this partial table. So if I want to figure out the slope, right, I need to know the change in y divided by change in x. And I could, for example, say, hey, what's 22 minus 16? And then divide that by 7 minus 6. Oh, that's a change of 1. So this is going to be pretty straightforward, right? So let's look at our slope. Change in y is 22 minus the number 16. And then down below for change in x, I'm just going to write 7 minus 6. Well, 22 minus 16, 16, 17, 18, 19, 20, 22, it's 6. Right? 22 minus 16 is 6. And 7 minus 6 is 1. So it looks like my slope is 6. Every single time x increases by 1, y increases by 6. And actually, now that I look at this, yeah, that's plus 1, plus 1, plus 1. So my x's are all going up by 1. 10 plus 6 is 16. 16 plus 6 is 22. 22 plus 6 is 28. Totally convinced I have the right slope here, right? Rise over run, change in y over change in x. The slope m is the number 6. Then I need to figure out my y-intercept. And I can do it a couple ways, right? I can extend this table backwards. But the other thing I could do is what I did above, right? Hey, if y equals mx plus b, then certainly y minus mx will give me b. So I can pick any y in this table, right? Any y that I want. I'll pick the very last one. So I'm going to grab the last y, which is 28. And I'm going to use the x value that goes with it, which is 8. And I know that my slope is the number 6. And I'm just going to plug them into this, right? So I'm going to write down what? 28 minus 6 times 8. Okay, 28, 6 times 8 is minus 48, right? 6 times 8 is 48. Is B. It looks like B is it negative 20? B is negative 20. I'm going to 28 minus 6 times 8. Looks like B is negative 20. So I've got my y-intercept, right? My y-intercept is negative 20. My slope was 6, so I'm ready to write the answer. The equation here is y is equal to 6 times x minus 20. Now, what's nice about this particular problem is there are lots of values I can run through to check and make sure this is working. In fact, I want to remind you of one of the tools we've discussed in class. It's called the table tool. So if I go to table, it says enter a function. I'm going to enter the function 6 times x and then minus the number 20. Press enter and it says, okay, I'm going to start at the number 0. I'm going to increase my x's by 1 and I'll do that automatically. So I'm just going to take all that. So enter, 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 and then go. So if I look at it, when x is 0, you can see y is negative 20, which is perfect because that is the y-intercept. And you can see that 1 would give me negative 14, 2 would give me negative 8, 3 would give me negative 2. But here's where it gets interesting. There. 5 gives me 10. Yeah. 6 gives me 16. 7 gives me 22. And 8 gives me 28. So what I'm doing is I'm looking at this table and every single value, right, that I see showing up on my calculator is confirmed on this table. So without a doubt, this is the answer, y equals 6 times x minus 20. Next question says, hey, here is a function. Here's a function. Please evaluate this function. Boy, okay. So I can see that 3 is the input into this function, and it's going to have to land here and here to evaluate this. So this is going to become, open parentheses, 3 times another 3 plus a 1, close parentheses, open parentheses, and then I've got this x3 and then plus a 2, close parentheses. So if I evaluate this first set of parentheses, I've got 3 times 3 plus 1. 3 times 3 is 9 plus 1 is 10. And in the second parentheses, I've just got 3 plus 2, which is 5. So I'm looking at 10 times 5, which is the number 50. So what does that mean? That means that when x is 3, y became the number 50. I do have ways that I can do this on this particular calculator too that are probably worth knowing about. So if I quit all this, I can say, look, 3, I'm going to store that into x. Boop. Now that I've done that, I'm just going to evaluate the following. Open parentheses, 3x plus 1, close parens, open. And I'm going to have an x plus the number 2, close it, and it says 50. I like doing it by hand, but it's nice to see that I could use this calculator to evaluate this also. This right here was a very commonly missed problem, and I know why this was missed often. It's missed often because of a misunderstanding of what's getting squared. So if you look at this, x is the number -4, and this problem says you need to take that x and you need to square that. So how I show that is like, this is the x, and I'm going to square exactly that. -4 gets squared, and then after I have that, I'm going to add the number 4 to that. So -4 times -4 is +16. And this is the thing that's kind of confusing. And I'm not sure if it's calculator use, that's incorrect calculator use. I do want to point this out. If I was to type on my calculator, hey, -4 raised to the second power, I want you to understand how your calculator interprets this. It does not see this as a -4 getting squared. It sees this as the opposite of 4 squared. 4 squared is 16, so it's always going to tell you that this is -16. But that's not what we have here, because we were not asked to find the opposite of 4 squared. We were asked, what is x squared when x is -4? So if you want to evaluate that properly in your calculator, you need these parentheses. So open paren, here's the -4, close the paren, and now I can square that. That is properly -4 times -4, which is +16. Another option is you can say, hey, -4, I'm going to store in x. My calculator now thinks that x is -4. If I take x and I square that, right, and then to that, I can add the number 4. It gives me exactly 20. So 16 plus 4 is 20. The answer here is this should be 20. Let's go to the second page. On our second page, it was backwards. Oops, up here. It says, hey, now what I'm asking you is, what is the input value, right? What value of x is going to make this function equal the number 80, right? What value of x? So to do this, I'm just going to take the definition of the function, right? F of x is defined as 4 times x plus 2 times the quantity of x minus 20. And I'm going to set that definition equal to 80. Now that I've done that, now that I've set that definition equal to 80, I'm just going to solve for x, and it'll tell me the value of x that makes this become 80. So I'll rewrite part of it, 4x plus 2x minus 40. Right, I distributed that 2 to both the x and the -20, and that equals 80. 6 times x minus 40 is 80. And if I add 40 to both sides, I get 6 times x is 120, not 1,000, not 1,200, but 120. And then finally, x is 120 divided by 6, which should be 120 divided by 6. Should be 6 divided by 12 is 2. It should be 20. X should equal the number 20. I believe X is 20. Let's check this, right? If X is 20, it should do something predictable. If I have a 20 that goes into here, and if I have a 20 that goes into here, what does this become? Well, in the first part, it becomes 4 times 20, which is the number 80. Yeah. Plus, over here when X is 20, this becomes 20 minus 20, which is 0. And 0 times 2 is 0. So it becomes 80 plus 0. So guess what? When I put 20 into this function produces an output of 80. So 20 is my value of X, right? The answer is 20. When X is 20, this function becomes 80. One more like this, very similar. Again, I'm being asked what is the value of X, so I'm just going to take the definition of this function. This is 8x plus 1. Set it equal to the desired output. 8x is 16 if I take away 1 from both sides. And when I divide both sides by 8, I get x is 16/8, which is the number 2. So when I give this function the number 2, it should produce 16. And yeah, you can confirm that. 8 times 2 is 16, and 16 plus 1 does indeed produce an output of 17. So 2 is the correct output. All right, let's look at next question. It says simplify each expression. So when we're looking at this, guys, simplification means we do not want any lingering giant ones. We do not want any negative exponents left in our final answer. This monomial, right, the one thing I notice is that it does have some factors of y scattered. And it turns out that if I combine -4 and 6, I do get 2. So I believe the answer is 6x to the 5th times y squared. There are ways that we can kind of check this. We can certainly check to see if we're wrong. It's more difficult to assert that you're correct, but I can say that we're correct for a couple of reasons, right? One of them is I know the laws of exponents, right? So it is true that if your bases are the same, both bases of y, because these are both y, and I'm multiplying here, I can add these exponents as a shortcut. So when I add -2 and I add 6, I do get positive 2. So let's just leave that one. 6x to the 5th times y squared. Next question. Oh, this is great. So there's some giant ones here that we're gonna rewrite this. I'm gonna choose to rewrite the numerator as 3 times 7. I know that is equivalent to 21. And I'm also gonna break up this x to the 10th power. I'm gonna write that as x to the 10th, or rather x to the 8th times x squared. And I do know that x to the 8th times x squared is exactly the same as x to the 10th, right? So this is nothing more than x to the 10th, and 3 times 7 is nothing more than 21. So I haven't changed this at all. I've just rewritten it to a different form. And the denominator, I had 7x to the 8th. Now you can see the way that I've lined this up. It's very easy to identify the fact that there is a value of 1, right? And what I'm left with is in the numerator, in the top, I have a factor of 3, and I have 2 factors of x. So I have 3 times x squared. In the denominator, you can see this giant 1 is in there, right? It's just the number 1. And because that 1 is in the denominator, I can just go ahead and write this. My final answer is 3x squared. So 21x to the 10th over 7x to the 8th is 3x squared. Let's look at part C. Part C has 3 of these 4x to the 2nd power, right? So I've got a 4x squared times 4x squared times 4x squared. By the way, I could write this as this is the same as 4x squared to the 3rd power, but this is the expanded form of that. 4x squared, 4x squared, 4x squared. Using the commutative property of multiplication, right, I could totally write this as a 4 times a 4 times a 4 times an x squared times an x squared times an x squared. When I multiply x squared times x squared times x squared, that's 1, 2, 3, 4, 5, 6 factors of x. So that's x to the 6th. 4 times 4 is 16, and 16 times 4, is that 64? 16 times 4 is 64, yeah. So 4 to the third power, or the number 64. So I guess I'd leave this as 64 times x to the sixth power. 64x to the sixth. They're the same. And then my last question is 2x to the fifth times, or over x to the negative fifth. So one point of confusion is, if this was x to the fifth over x to the fifth, that would be a giant 1 and we'd be finished, right? The problem that we have is that this denominator is not x to the fifth. This denominator is x to the negative fifth. One of the things we've talked about, and we'll keep talking about more, is we have this ability to get rid of negative exponents just by multiplying them by something. So if I was to multiply this denominator times x to the positive fifth, notice what this would do. I'm just saying, if it was if there was a magic way I could do this, notice what would happen with this denominator, right? If this was multiplied, this would become x to the negative fifth plus 5, which is x to the 0, which turns out to be the number 1. So by me taking and multiplying x to the negative fifth times x to the positive fifth, I literally wiped out that negative exponent. It's gone. It's now just the number 1. Now, the truth is, I cannot just arbitrarily, you didn't see all my work there. The truth is, I cannot just arbitrarily decide that I'm going to multiply the denominator only by x to the fifth. However, we do know that if I was to match that in the numerator, and in the numerator I was to put an x to the fifth up there also, what am I really multiplying by? Well, I'm multiplying nothing by nothing but the number 1. So multiplication by 1's magical. I can choose to multiply by 1, and I'm not going to change the value of this expression. I'm just going to change its format. And you can see what it's done with the denominator, right? It's made the denominator just the number 1. In the numerator, what do I have? I now have 2x to the fifth times a new x to the fifth, right? That's this x to the fifth. And I said, as we said in our denominator, we just have the number 1. We can simplify this, right? This whole thing is nothing more than 2x to the 10th power over 1. So 2x to the 10th power is the simplified version of this expression. And I think we're ready for, oh yeah, last question on this page. It says solve each equation below for the given variables. Okay. So just looking at this equation, I think it would be much more simpler for me to solve if I was to rewrite the left-hand side. So I'm going to rewrite the left-hand side as that's 3 times x, right? That's an x plus an x plus an x. Addition is repeated multiplication. So x plus x plus x is 3 times x plus a 5 equals 2x plus 20. If I was to take away 2 x's from both sides, this side would become just a plain old x, right? 3x minus 2x is x plus 5. Take away 2x from this side, it's going to be 20. And then if I subtract 5 from both sides, I get x is the number 15. I don't doubt it for a minute, but if I've got extra time, why not check it, right? So I can easily check this by just taking 15 and storing that in x. And I can type the following. Hey, what is x plus x plus x plus the number 5? Boop. It makes 50 on the left-hand side. On the right-hand side, I've got 2x plus the number 20. Guess what that is? Boop. It's 50 also. So when x is the number 15, both the left-hand side and the right-hand side become 50. So this is most definitely, boop, the solution. X is 15. Next problem we have is, this also would benefit from a bit of rewriting. So if I just consider that first term, x to the 4th, that's 4 factors of x over 3 factors of x. And if I was to look at that in terms of a giant 1, there's just a single x in the numerator. So that whole first term is nothing but x. So I can rewrite this thing as x plus 2x plus 22 over 2 is 11 equals 44. That is equivalent to 3x plus 11 is 44. That means that 3x is 33. And if I divide both sides by 3, 33 over 3 is what x is. And I believe that's 11. So x is the number 11. X is 11. And I can check that even in the original equation, even though I don't like that x to the fourth, x to the third, I'm not worried about that because my calculator is going to handle it. So let's go ahead and store 11 into x. So 11 store x, boop. I'm going to look at a fraction in the numerator. I'm going to type x to the fourth power. In the denominator, I'm going to type x to the third power. And the next thing I'm going to do is going to add 2x, and then I'm going to add 22 halves. Now, the reason why I go back to the original expression all the way is I'm trying to detect if I made some mistake in one of my steps. And I don't know. I asserted that 22 over 2 is 11, but I'm wrong. Maybe I'm wrong, right? I asserted that x to the fourth over x to the third is really just x, but maybe I'm wrong. So that's why I go back to the original expression, because if anything is messed up here, I'm going to consider the whole thing. When I do press enter, I do get the number 44, and it turns out 44 was exactly what I had on the other side. So this whole mess became 44 when x was 11. X is 11 is definitely the solution. All right, we're on to our last page. This is the second point. No, actually, that's part B. Let's look at part A first. So part A has a times b squared. So look, when I do substitution in, especially if there's negative numbers, I always use parentheses. So there's a, and I'm going to multiply that by b, which is 2 to the second power, minus 16, and then minus the number 12. That's the numerator. In my denominator, I have 5 times 2, 5 times 2, 5 times 2. So let's simplify. This numerator is negative 4 times 4. So I'll write negative 4 times 4. That's what 2 squared is. Minus 16 minus 12. And in my denominator, I have 5 times 2, which is the number 10. So I'm looking at negative 16 minus 12. Let's try this here. Negative 16. No, clear. Negative, no. I gotta, oh, I know, I didn't do this. Negative 16 minus 16 minus 12. That's my numerator. And then can I just hit a fraction key? Negative 44 over 10. Oh my goodness. Did I get what? How's that a possibility? Let me press enter. I just learned something recently. If I press enter, or no, if I press clear, it puts my cursor where the error is. The error is I typed subtract 44. I have to hit negative 44. That's perfect. So negative 44 over 10, this is negative 44 over 10, is the same as negative 22 over 5. And if I wanted to, I could press this double arrow thing and it would kick this into a decimal, so which is apparently the same as negative 4.4. I'm interested, like I might want to try to do this if I have extra time, try and do this a different way, check it again, but I'm pretty confident that's negative 4.4. Last problem we have on this group. This is question 6, part B. This was the one where we saw some errors, and it's the same thing about squaring this negative 4. So again, if I use parentheses, right, plus 5 times something, and then minus something. So if I use parentheses, I can say, look, negative 4 is going to go in these parentheses, okay? 2 is going to go in these parentheses, and then 12 is going to go in these parentheses. So using these parentheses will help me use the right notation that will be accepted by my calculator. So negative 4 is going to get squared, plus 5 times 2, and then minus the number 12. Negative 4 squared, that's negative 4 times negative 4, which is positive 16, plus 5 times 2, which is 10, minus 12. 16 times 10 is 26. And then 26 minus 12, I believe, is the number 14. Yeah. And again, just I don't know. Open paren, -4 is going to get squared, and then I'm going to, what? Add 5 times 2, and then I'm going to subtract the number 12. This should give me 14, and it does. Right, final question. Oh, nope, I lied. Final two questions. First one, it says, Mr. Roberts and Mr. Woolard are racing their tricycles on the Shasta track because Mr. Roberts is older and slower. He is generously given a 4-meter head start, and he travels at a speed of 3 meters every 2 seconds. So we've discussed head starts quite a bit. And it turns out if you have a head start, that means when they say on your mark, get set, go, you are not at the starting line, right? You're not 0 distances from the starting line. You're 4 meters from the starting line. So a head start corresponds to this. I'm way down the track, 4 meters in the lead as soon as they say go. And I'm traveling at a speed, let me get rid of this calculator. There you go. And I am traveling at a speed of 3 meters every 2 seconds. So once I've got this, I'm just going to go up 1, 2, 3 meters and then over 2 seconds. Up 1, 2, 3 meters over 2 seconds. And I could do it again-ish, right? So that looks like roughly the graph for Mr. Roberts. For myself, I am Mr. Roberts. I am that old guy that's slow. And I'm going to go ahead and line this up and just drag little red line through there. So that's my race. And if I was going to write the equation for that, because I'm asked to, that equation is y is equal to up 3 over 2 times x, plus I have a head start of 4 meters. The other racer does not need a head start, but the guy's a little bit like, he's like, there's no way I'm going to lose this. In fact, I can stand right here at the starting line for the first 3 seconds. So he's like, during the first 3 seconds, he does not pedal at all, right? Mr. Woolard does not pedal for the first 3 seconds. So you can imagine right here, he is at the starting line, but watch what happens. On your mark, get set, go. They say go, the gun fires 1 second, and he has not moved. We saw this when we were looking at the walking the line in the classroom. Another second, he still has not moved. He's still exactly holding still. 3 seconds, he's still not moved. At this point, he begins, right? This is the first point where he begins. And how does he move? He moves 5 meters every second. So I'm going to go up 1, 2, 3, 4, 5 meters over 1 second. Up 1, 2, 3, 4, 5 meters over another second. And that's enough. I'll grab my ruler, line it up. And it looks like this would probably be an okay line. So I'll do this one in green. Now, the thing that's tricky about this equation for Mr. Woolard is we do know that y is equal to 5x is part of it, but he doesn't have a y-intercept at 0, right? He doesn't start moving at 0. In fact, he doesn't have a y-intercept at 3 either. His x-intercept's at 3. If I continue this line downwards, somewhere way down there, we're going to see that he has a y-intercept, and it's like a negative number, effectively. The question is, what is that y-intercept? Well, here's what's nice. I do know his slope, m, and I'm certain of several points, right? I know that when x is 3, y was at 0. I know that when x is 4, y was at 5. And I know that when x is 5, y was at 10. So I know a lot of xy pairs that are on his path. I can use any one of those to figure out his y-intercept. Remember, this is our thinking. Hey, since y is mx plus b, if I need to figure out b, I could just take a y and subtract m times x. Okay, m times the corresponding x. So I'm just going to pick this one because it's close. I'm going to look at this x, and this y. So my thinking is I'm going to take x is 4 and put it in for x. I'm going to take y is 5 and put it in for y. And we know his slope was 5, right? Yeah, it was up 5. His slope is 5. So I'll put that in for m. So here's what we get. We get 5 minus 5 times 4. Not 40. 5 times 5 minus 4. Y, which is 5, minus the slope 5 times x, which is 4. So 5 minus 20, which is the number negative 15. Now, I could have picked any one of those points. I could have picked the 3, 0, the 5, 4, the 5, 10. But what I know is this. I know that his y-intercept had to be negative 15. And then this equation now satisfies everything. So if I put, for example, 3 seconds into that, when I put 3 seconds into it, you can see that my distance from the starting line is 0 because I'm still at the starting line when I start. And then another 3 seconds, you can see that I'm at, if I put in 4 seconds, you can see that it would give me 5. And if I put in 5 seconds, you could see it would give me 10. So that's both equations, and that is both of the graphs of the lines. Final question. In another race, Miss Fifield, she teaches CP Math 2 here at Shasta High. By the way, Mr. Wooler does teach honors Math 2, and he's a great teacher. I hope you get to have him someday. Fifield is a phenomenal teacher also. She teaches, most years she would teach honors Math 2 and CP 2. This year she's just teaching the CP 2, and probably she'll be back doing a couple sections of honors again next year. Anyways, great teachers, high respect for both. In another race, Miss Fifield travels at 12 feet per 1 second. I'm going to write that down. She's traveling 12 feet per second, and I'll just say per 1 second, or I could just say 12 feet per second. And I'm asked to convert this into miles per hour using giant ones. So I know what this looks like. I want seconds to go away. I want seconds to become hours. And I know that if I want seconds to leave, right, I have to put seconds in the numerator because currently I have seconds in the denominator. And the other thing that I know is I know that 60 seconds is the same thing as 1 minute. So this is a good first step. What I am multiplying by is a number 1. It doesn't look like it, but because of the units, right, understand 60 seconds is the exact same amount of time as 1 minute. So yes, I'm legitimately multiplying by just the number 1. I'm going to multiply by another number 1. This time I want my minutes to leave, so I'm going to point out that, hey, 60 minutes, right? I had minutes in my denominator, so I'm putting minutes in my numerator. 60 minutes is the same thing as 1 hour. Now, part of my mission is accomplished, right? I now correctly have hours for my unit of time. I've gone from seconds to hours. Last thing I need to do is I need to get rid of these feet, and I need to turn the feet into miles. We've talked about this conversion number, right? And you don't have to have this memorized. This is the kind of thing I would often have written on a whiteboard. But one mile is 5280, right? 5,280 feet. So you can see currently feet are up in the numerator. They're up in the top here. So I'm going to put feet in the denominator. And I'm going to put 1 mile in the numerator. 1 mile is the same as 5,280 feet. Again, this is a giant 1 because they're equal distances, right? A mile is the same distance as 5280. Something divided by itself is 1. So look at this. I've got 12 feet per second. I multiplied by a giant 1 times another giant 1 times another giant 1. And we know that if we multiply by 1, right, we don't change the value of something. We're just going to change its format. Now let's do the dimensional analysis. So in terms of time, right, these seconds are going to be canceled by these seconds. So I no longer have seconds in this problem. The minutes are going to be canceled by the minutes. So I no longer have minutes in this problem. And then finally, I've got the feet, right, from the original part are going to be canceled by feet down here in the denominator, way at the end of this. The only 2 units I'm left with is I'm left with miles in the numerator and hours in the denominator. So those are the units of my answer. Now, what is the answer? Well, in my numerator, I've got 12 times 60 times another 60. And in my denominator, I've got 5280. So I think my calculator is calling me. Let me grab the calculator. So if I'm looking at this calculator, I'm going to go ahead and grab a fraction. Why not? Looks clean. 12 times 60 times 60. Okay. And then in my denominator, I'm going to place 5280. There we go. 12 times 60 over 5280. And I get 90 over 11. So this is the same as 90 miles per 11 hours. I want this as a unit rate. No one says, how fast are you going? I'm going 90 miles per 11 hours. What? I said I'm going 90 miles per 11 hours. Okay. That is the same as, and I just hit this double arrow, that's the same as 8.2. It's about the same as 8.2 miles per hour on Mrs. Fifield's tricycle. Was she in a tricycle? Doesn't say. I think we're all in tricycles. She's riding on a tricycle. 8.2 miles per hour. 8.2 miles per hour. All right, class, that's it. That is the study team test. Of course, we're doing our homework each night because a lot of our homework that we're seeing at the beginning of chapter 3 is like some of the questions we've encountered here and like some of the questions we will encounter on our test on Friday. Please feel free to watch this video more than once if you've got questions. I look forward to talking to you in class. This is Mr. Roberts. I hope you have a great afternoon, evening, and I look forward to seeing you tomorrow.